Hello, pre-calc honors students. Here are with the sum and difference formulas for tangent. Again, you can't just distribute tangent over subtraction. So let's derive the formula first by looking at what we did with sine and cosine of alpha minus beta from the last section. Sine of alpha minus beta, that's sine alpha cosine beta minus cosine alpha sine beta all over cosine of alpha minus beta, which is cosine alpha cosine beta plus sine alpha sine beta. And now we got to do something kind of tricky. We got to take this expression and multiply the top and bottom by just the right thing to get things simplified here. Let's see what we can do with this. What if we multiply the top and bottom by 1 over cosine alpha cosine beta? 1 over cosine alpha cosine beta. What that does then is you got to imagine this denominator in each one of these. So let's make a little more room for this proof. So we get sine alpha cosine beta all over cosine alpha cosine beta minus cosine beta sine beta all over cosine alpha cosine beta all over cosine alpha cosine beta all over cosine alpha cosine beta plus sine alpha sine beta all over cosine alpha cosine beta. And you can see a lot of things cancel. Here the cosine betas cancel and we get sine alpha over cosine alpha. Here the cosine betas cancel and we get sine beta. I'm sorry, I wrote down something wrong here. We must make a little precise fix here. This was cosine, yeah, I made it wrong over there too. This is cosine alpha, there we go. And so same thing over here. This is cosine alpha. Sorry about that. Oh, and because I copied that, that's not going to let me erase it. Okay, so cosine alpha. So let's continue over here. The cosine alphas cancel, and we end up with sine beta over cosine beta all over these cosine alpha, that's one, so you get 1 plus sine alpha over cosine alpha times sine beta over cosine beta, and the whole thing boils down to tangents then. Sine over cosine is tangent. Tangent alpha minus tangent beta over 1 plus tan alpha times tan beta. Great. So that's two formulas. Tangent of alpha minus beta is tan alpha minus tan beta. It almost looks like you're distributing, but you're not. It's over 1 plus tan alpha times tan beta. And the tangent of alpha plus beta, tan of alpha plus tan of beta over 1 minus tan alpha times tan beta. Okay, so let's try this in finding the exact value for tangent of 15. Well, we can look at it as the tangent of 45 degrees minus 30 degrees. So we get the tan of 45 degrees minus the tan of 30 all over 1 plus tan 45 tan 30. And you should know all these special values for the tangent. 45, tan of 45 is 1. Tan of 30, that's the shallow one, so that's 1 over root 3. Over 1 times root 3. So I'm going to multiply top and bottom by the square root of 3. And that gives me square root of 3 minus 1 all over square root of 3 plus 1. Can multiply by a conjugate. Square root of 3 minus 1 over square root of 3 minus 1. So now we get 3 minus 2 square root of 3 plus 1 all over 3 minus 1, or 4 minus 2 root 3 all over 2, or 2 minus the root 3, giving a number that's slightly positive, and that's what we expect for a tangent of a 15-degree angle. Something positive but small. And sure enough, you can go again to that table I talked about last section. And if you focus on the tangents, you see quite a few, but look at this pattern here. So basically, when you take the tangent of the k pi over 12s, these new ones I'm adding to the special angles, you get plus or minus 2 plus or minus the square root of 3. So notice down here at 285, which is, if you look at 285 on the unit circle, that's past 270, just 15 degrees beyond past 270. Now it's in the fourth quadrant where the tangent's negative. And it's that really steep negative slope, so I make both the quantities negative to get our lowest possible value for k pi over 12 tangent. Now, suppose tan alpha equals a third and tan beta equals a half. Find the tangent of alpha plus beta. Well, we can go ahead with tan alpha plus tan beta. Notice we can do this without actually coming up with the angles alpha and beta. And you can expect to do this on this test without a calculator. Over 1 minus tan alpha times tan beta. So that's 1/3 plus 1/2 over 1 minus a third times a half. Or a third plus a half over 1 minus a sixth. The LCD here equals 6, and so I'm going to do the special compound fractions trick with the LCD of multiply both numerator and denominator by 6 to get 2 plus 3 over 6 minus 1, 5/5 is equal to 1. So we get it, it's equal to 1. Now it's going to help us with the next part. Show that the inverse tangent of a third plus the inverse tangent of a half equals pi over 4. Well, you see where this inverse tangent comes from? Let's let alpha equal the inverse tangent of a third. And tan alpha then equals a third. And let beta equal the inverse tangent of a half. So the tan of beta equals a half. And essentially we're trying to show then that alpha plus beta equals pi over 4. Well, from this last problem we showed the tangent of alpha plus beta equals 1. And where does that happen? Only here or down here in this quadrant? At pi over 4 or at 5 pi over 4? Now that's not possible if both alpha and beta are essentially first quadrant angles, because if I define it this way, it's inverse tangent of a third, that only gives an angle between negative pi over 2 and pi over 2 by the inverse tangent range rule. And since it's positive, it must be in the first quadrant. So therefore, alpha plus beta equals pi over 4, and therefore then inverse tangent of a third plus inverse tangent of a half equals pi over 4. Now, angles between lines. Remember how we said that the tangent of the angle of incidence, that is the angle that a line makes with the x-axis, is equal to the slope of that line. So here's line 1 with a slope of m1. And here's line 2. Remember, here's beta, and the tangent of that angle beta will equal the slope of this, and here's line 2. And we can actually come up with alpha plus beta. Let's put it in here. Alpha minus beta then is this minus this, is this angle in here like this. So there's alpha minus beta, that corner right there. And if we look at the tangent of alpha minus beta, we get the tan of alpha minus the tan of, oopsie, hello, the tan of alpha minus the tan of beta all over 1 minus plus tan alpha times tan beta. We just talked about how tan alpha was equal to m2, slope 2. And tan beta, slope 1. And tan beta is equal to slope 2 all over 1 plus m1 times m2. So here's a little trick for finding the angle between two lines if we know their slope. So find an angle between these lines. Well, the tangent of the angle between them, alpha minus beta, will equal slope 1, which is 3, minus slope 2, which is negative 2, all over 1 plus slope 1 times slope 2. So you get 5 over 1 minus 6. That's 5 over negative 5, so that's negative 1. So, when is the tangent equal to negative 1? That's in the second quadrant or the fourth quadrant at 135 degrees or negative 45 degrees. And so we could say the angle between the lines is 135 degrees, or since we're just measuring the positive angle between these two, we could say 45 degrees as well. Okay, and now I just want to verify that with a quick example from GeoGebra. Okay, here we're in GeoGebra, and we want to look at 3x plus 1. That's one of our lines. And we also want to look at 5 minus 2x. There's the other line. And we want to come up with the angle between these two. So to do that, you can just ask GeoGebra to measure the angles. And measure the angle, select 3 points or 2 lines. So we can actually just select these 2 lines. Click. Well, first of all, we've got to get this. Measure the angle, select that line and that line. Sometimes you have to just come over here and select them this way. Let's go like this. Sometimes GeoGebra can be a little iffy here. I'm on measuring the angle, select this line. Okay, hold the bus here. Let's go like this. Okay. Get the angles between these 2 lines. You know, it might be that it's treating these 2 things as functions and not lines. So we can turn them into lines in many ways as opposed to functions. We can find the intersection of those 2 things, intersect the 2 objects, this object and this object. So that's going to be a key point there where they cross at 0.8, 3.4. Let's get a little more accuracy going here under options, rounding. I think it took that. Yeah, okay. And now let's get some other points on the object there so we can come up with the angle. Let's put a point on there, a point on there, and now we can just select 3 points to do our measurement. Angle, select these 3 points, boom, boom, boom. There. Now it's giving 225 degrees. So I'm going to undo that and select them in the other order so it gives me there, that angle of 135 degrees. And of course you also get its supplement is 45. You could say then the angle between these is either 135 or if we want to measure the supplement it's 45. Okay, so let's wrap up now with one last example. We are rolling, right? Yes. Here we're going to find the exact values of these tan 15 plus tan 30 over 1 minus tan 15 tan 30. Well, rather than coming up with that tan 15 answer and getting really complicated expressions here, we can see that this is the expansion of the tan of 15 degrees plus 30 degrees. That makes it so much easier. Tan 45 degrees, and that's equal to 1. If someone would like to take our tan 15 answer from before and plug in with the tan 30 answers and simplify all that down, I think that'd be amusing and worth a pip. Same thing here, we could write this as the tan of 85 degrees minus 25 degrees. So it's the tan of 60, and that's one of the measurements you looked at before there. That's that steep slope for the tangent. That's the square root of 3. Okay.